Hello everybody, let's start the second segment of our lecture on property testing. We are interested in designing an algorithm and analyzing it to test whether a given graph is connected, and recall that the graph will be stored in some sort of a cloud, so we will not have full access to the graph, rather we will have access to the graph via queries, and in particular we have three types of queries that we can send to the cloud. The first query will request a random node in the graph. The second query requests for the number of neighbors of a particular node V, and the third query requests for the say the fifth neighbor of a particular node V. Okay. These are the types of queries that we can make on these in this large graph stored in the cloud, and the cloud will respond with the appropriate responses, and we need to test whether this graph is connected with as few queries as possible. Of course, when the graph is connected, we want to accept it. Normally, property testing only requires us to accept this scenario with probability at least 2/3. In our context, however, we are going to design an algorithm that is always going to accept a graph if it is connected. So, in other words, this algorithm that we are designing is going to have a one-sided error. If, however, the graph is far from being connected, the algorithm we are going to design now will reject the graph with probability at least 2/3. And what does it mean for a graph to be far from being connected? Well, this fits in with the notion of being far from having a property that we've already discussed in the first segment. A graph is epsilon far from being connected if at least epsilon m edges must be added to establish connectivity. So, the graph is highly fragmented if it is epsilon far from being connected, and in order to defragment it, if you will, and get the graph to be connected, we will have to add edges, and in particular we will have to add epsilon m edges in order to establish connectivity. There is one little aspect of this that we need to note. Let's assume that epsilon is fixed, and let us assume that the graph is epsilon far from being connected. Then we can conclude that the number of edges is only of the order of n. Now, why is this the case? Suppose not. Now, suppose m is little omega of n. In this case, epsilon m is also going to be little omega of n, in which case we immediately notice that this epsilon m number of edges is going to be sufficient for us to get the graph to be connected. So, such an so we simply cannot have a graph that is epsilon far from being connected having a number of edges that is little omega of n. So, as a result, we can safely assume that we are dealing with a sparse graph with at most O of n edges. Our goal is, of course, to minimize the query complexity, basically the number of queries that we need in order to be able to answer whether the graph is connected or not. The main philosophy behind our algorithm is the following. We're going to assume the sort of innocent until proven guilty paradigm of thought, meaning we're going to assume that the graph is connected and we're going to seek evidence that it's not connected. And until we find such evidence, we're going to say that the graph is connected. And when we do find some evidence not connected, that's only then will we say that the graph is not connected. As a consequence, this the algorithm that we design will always be correct when the graph is connected, because we cannot find evidence that it's not connected. So and moreover, if we say that the graph is disconnected, then we will only say that it's disconnected when we have clear evidence that it's actually disconnected. Okay, so let's dig a little deeper and look at the intuition behind the algorithms. If the graph is epsilon far from being connected, then the graph will contain a lot of small components, because a lot of edges need to be added to the graph before we can get it to be connected, which means that the graph is very, very fragmented. Okay? And because the graph is fragmented, we want to be able to say that not only are there lots of components, there are lots of small components. And so a random sample into the set of vertices could very well, with a good probability, land us on such a small component. Now, if we land on such a small component, then we should be able to find evidence for this graph being disconnected, because if we land in a small component, a very small BFS should tell us whether we are in a small component or a large component. And if we are lucky enough to land in a small component and we perform the small BFS, we should be able to prove the guilt, meaning we have been able to prove that the graph is disconnected. And this is the main intuition. So let us look at the algorithm in greater detail. So the algorithm is an iteration over a set of steps. For now, I would let us ignore the number of, or at least let's not get distracted by the number of repetitions. So we're going to perform some number of repetitions, and each repetition is the following. We're going to pick a vertex V uniformly at random, and this is done under the hope that our random choice will land in a small component. And from that vertex V, we will perform BFS, visiting at most some number of vertices, and this is designed to be, this is our notion of small. We will formalize these things shortly. So we perform a BFS and that visits at most these many number of nodes. If the BFS terminates, that is, if the BFS queue becomes empty, that means we have actually reached a small component, in which case we will reject G, because we now know that the graph G is disconnected. Now, after these many repetitions, if we are not able to find any evidence at all that the graph G is disconnected, then we will come out of the loop and we will accept G. Okay, so this is the algorithm, and as you can notice, the algorithm itself is very, very simple. We now have to formally prove that our algorithm indeed accepts all connected graphs and rejects graphs that are far from being connected. So in particular, this is the theorem that we need to prove. The connectivity testing algorithm requires O of n cubed over epsilon cubed m cubed number of queries. And just a quick note about this, when m is O of n, the number of queries is actually only O of 1, assuming epsilon is a fixed constant. Now, with that many queries, our algorithm, we need to show that our algorithm is always correct when G is connected, and it is correct with probability at least 2/3 when G, the graph G, is epsilon far from being connected. This is the theorem that we are going to prove, and the overview of the proof is as follows. It's quite obvious this algorithm is always going to be correct when the graph is connected, simply because it cannot find any evidence of being disconnected. So our focus therefore is going to be on graphs that are epsilon far from being connected. So the sequence of steps in this proof is as follows. First, we will prove that there are lots of components in the graph G if it's epsilon far from being connected. And then we will go on to show that many of those components are actually small. And we'll of course define small quite precisely. And then we'll go on to show that our randomly chosen V is likely to be in a small component, therefore leading us to the evidence that we are seeking. And we will, in the third step, we'll work out the probability with which we will land in a small component, and therefore the probability with which our overall algorithm is going to be correct. So this is the overview of our proof. So let us go on to the first step in this proof sequence. Our first lemma is to show that if the graph G is epsilon far from connected, then G has lots of components. And we've illustrated that by this figure that shows all these components. And here's the quick intuition. If it is epsilon far, then we are required to add at least epsilon m edges before the graph can be connected. And now if there were very few components, we can simply string them together as shown in this figure, and we should be able to connect the entire graph. So the proof relies on quantifying the number of such edges that we can add, and therefore the number of components that that the graph should have. So let's be a little bit more formal now. If the graph G is epsilon far from connected, then G has more than epsilon m plus 1 connected components. And the proof is as follows. Suppose not. That is, if the number of connected components is at most epsilon m plus 1, then at most epsilon m edges suffice to string the components together and therefore get them to be connected. But this would mean that the graph G is not epsilon far from connected, because epsilon far would mean that we have to we require more than epsilon m edges for connectivity. So this establishes the contradiction that we are seeking, and therefore we can conclude the lemma. Now that we know that a graph that is epsilon far from being connected has lots of components, we want to show that not only do we have lots of components, but moreover we want to show that we have lots of small components. Okay. Let's be a bit more precise with what we want. If G is epsilon far from connected, then more than epsilon m by 2 components. Now recall that there are at least epsilon m plus 1 or rather more than epsilon m plus 1 components in this graph, and we want to show that more than epsilon m by 2, about half of them at least, are small. And what do we mean by small? These are components that have no more than 2n over epsilon m nodes in them. Okay. let's go into the proof now. Again, we use proof by contradiction. Suppose not, that means there are at least epsilon m by 2 components that are large. Now, if there are fewer than epsilon m by 2 small components, then there must be at least epsilon m by 2 large components, and these are components with strictly more than 2n over epsilon m nodes. So, how many nodes are there in these large components? Well, let's work it out. It's going to be, well, we have at least epsilon m by 2 components, and each one of those components has more than 2n over epsilon m vertices in them. So, that is 2n over epsilon m. So, just that accounts for more than n nodes, and that is simply a contradiction again. So, the graph itself, we started off with only n nodes. So, we cannot have at least epsilon m by 2 large components, which means that more than epsilon m by 2 components must be small. So, with these lemmas in our background, we are now ready to prove the main theorem. So, just recall, more than epsilon m by 2 nodes are in small components, and each of these small components must have at least one node. Okay. Each one of these must have at least one node. So, what is the probability of a randomly chosen vertex V not being in a small component? Well, it must be at most 1 minus epsilon m by 2n. Okay. Why is that? Because what is the probability that we will vertex V will be in a small component? Well, each one of these small components has at least one vertex, and there are epsilon m by 2 such vertices at least. So, the probability of landing in such a small component is going to be greater than or equal to epsilon m by 2 divided by the total number of vertices that we have, which is, this is the probability of landing in a small component. So, the probability that V is not in a small component is at most 1 minus epsilon m by 2n. So, this is one particular vertex V that was chosen uniformly at random. If you recall the algorithm, we repeated this 4n over epsilon m number of times. So, what is so let us look at the probability that none of the 4n over epsilon m random nodes will land in small components. Now, this is really bad because we have missed all the small components, not once, not twice, but 4n over epsilon m times. So, this is a really bad event, but what is the probability of that bad event? Well, probability that it occurs once is 1 minus epsilon m by 2n, but 4n over epsilon m number of times means that the 4n over epsilon m goes to the exponent. So, if we apply this inequality 1 minus x is at most e to the minus x, this probability can be brought down to e to the minus 2. And of course, E being something like 2.71, so on, etc. It is easy to see that e to the minus 2 is less than 1/3, which is the probability that we will not find evidence. All our random vertex probes landed in large components, not in small components. So, we missed, this is the probability, this is an upper bound on the probability that we missed all the small components not once, twice, but all 4n over epsilon m times. And so this is the probability of missing. So the probability that our algorithm will correctly land in a small component and find evidence that we are in fact in a disconnected graph is therefore going to be at least 2/3. So that completes the part of the proof regarding the correctness of the algorithm. The number of queries is quite easy to show, and so that's going to be an exercise for you. So before we conclude, let's have a quick discussion on what we have studied so far. Just to remind you, when m is O of n, the number of queries is only O of epsilon to the minus 3, and if epsilon is also fixed, we are talking about a constant number of queries. And with this constant number of queries, we are able to with reasonable probability detect whether the graph is connected or epsilon far from being connected. And this works great. We're able to get a probability of correctness of at least 2/3, but it's actually not very difficult to get the probability of correctness down to a much smaller value. So for example, we can get the probability down to something of the form 1 by k for any arbitrary k value with just epsilon to the minus 3 with O of epsilon to the minus 3 times log k queries. So this will this will be a small exercise for you to show that this is in fact true. So with that, let us conclude the second segment of our lecture on property testing. Our third segment is going to be on linearity testing. Thank you very much.